In part 3 of fluid, electrolytes, and acid base, we're going to be taking a look now on page 996 at our water recovery in the kidney. So again, we have an increase in osmolality, which means the tonicity increases and we get somewhat dry in the tissues. And so as a result of that, we're going to have the stimulation, baroreceptors, etc., are going to get involved in the stimulation of ADH release from the posterior pituitary. This is antidiuretic hormone. Antidiuretic hormone is acting on the kidneys, and these are the collecting ducts of the kidney beyond the distal convoluted tubule for the most part. So in the collecting ducts themselves that are at first in the cortex, but then they drop down into the medulla all the way down to the minor calyx. And it's through that deeper area that we get aquaporin formation. And so I'm indicating here the aquaporin formation as a result of, these are transmembrane channels that allow for the water to pass through. And I indicated to you that when we're in the interstitial fluids, there's very little protein, there's very little tonicity, and we have to add tonicity. So we're, of course, in the kidney, we're adding the, we went over it the last chapter, we're adding sodium as well as urea, and there's a cycle in which we recover both urea and water. And water ultimately goes off into the plasma. Urea gets picked up again and reinserted into the interstitial fluid at the collecting duct. So ultimately we're going to retain water. And so the retention of water helps us maintain plasma fluid volume and reduces, with a little help from the beverages, reduces osmolality. There's not going to be much urine, though, unless we do some drinking. So that's that particular item right there. Again, they're just indicating here by this, how shall I say, fanciful diagram with the faucet, that a cell can release water to a highly tonic environment, right? So this would be a hypertonic solution outside of the cell. Here we would have a hypotonic solution in which there's very little tonicity and the cell actually picks up the water. So that's what's going on in that sensibility. Okay. Then they're indicating by the text here the whole discussion of both aldosterone and ADH. Aldosterone gives us the sodium concentration that's necessary so that when we have ADH to create aquaporins, the aquaporins will allow water to follow down a diffusion gradient with osmotic pressure wherever the sodium has gone. So water follows sodium is the intention here. So we retain water if we have a lot of sodium. People who have high blood pressure, of course, are encouraged to decrease sodium in their diet so they don't retain so much water so that their blood pressure is not spiked in any way and that their medications work well as a result. Okay, so then we have our next little discussion here, and we go over again, as I indicated to you, this is the cascade involving renin-angiotensin aldosterone is something that we have to, this is, I think, pretty close to our last experience of it, so we have to savor it here. Whenever we have high levels of potassium or low levels of sodium or hypotension, low blood pressure, what has happened is we're going to be acting upon the adrenal cortex and we're going to experience the release of aldosterone. Aldosterone will act upon the kidney's distal convoluted tubules and the cortical collecting ducts. And in fact, we identify here, and I don't know if you can read this, the chief cells of the cortical collecting ducts. Okay, and this would be above the arcuate artery out in the cortex area. So the chief cells of the cortical Okay, that's an important detail. It doesn't act down where ADH acts in the medullary region. It acts in the cortical region. And so the idea here is that we're going to reabsorb sodium so that we can have it as a constituent for water to follow, and we're going to exchange it for potassium. Potassium is viewed by the kidney as simply an extra ion to be used and is disposable from the point of view of the kidney, whereas the sodium by the kidney is viewed as extraordinarily rare and wonderful, even though we've since invented Safeway, but the kidney is living 50,000 years ago, so that's our situation. So we're going to balance out the levels of sodium and potassium as a result of that. Okay, we have the big overview here. What's going on with end diastolic volume? Remember, that is our regulatory point. And we're over here. This is an important diagram on page 1001. And here's our heart. They're indicating here that on the top of the diagram we have an increased stretch. So this is a rare diagram. Rarely do we actually look at the outflow of ANP. This is sort of like, oh, everything's working well, and we have good venous return. Apparently we didn't sit around too much. We had some good walks. We pushed the venous fluid back to the heart. We had a nice end diastolic volume. By increasing the stretch of the atria, that means that we're increasing our end diastolic volume, and we're having a really nice contractility and a really nice stroke volume. So life, from the perspective of the heart, is really good. And so we're going to release atrial natriuretic peptide. This is sort of the equivalent of singing in the shower or something. This is like, oh, happy days. Because now we have enough water and enough sodium, just the way we like it. And so that means that there's good cardiac output. Okay? So that's what's going on here, is that this is everything leading up to the things that we need to decrease the blood pressure, relax, have a good day. And what we're doing is we're turning off everything that has to do with renin-angiotensin-aldosterone. Okay, so we don't need as much sodium, we don't need as much ADH, we don't need as much renin-angiotensin-aldosterone, because life is sweet, and we have plenty of water, plenty of end diastolic volume. We've been exercising. The sodium in our diet is well balanced. Life is good. Okay, even aldosterone is decreasing. So that's the significance of ANP. This is the goal. This is when, that's an indication is, oh, I'm really happy. Okay. So, and again, this diagram, as you go over it in your book, it's fairly complex, and it covers all the bases here. But the idea is that when we have a decline in systemic blood pressure, we have all of these systems that come together to remedy the situation. Everything from the kidneys renin release, when we're going to have a double increase or double activation of angiotensin 1 to angiotensin 2. At the lungs, we have the ACE not inhibitor, that would be a drug. We have the angiotensin converting enzyme from 1 to 2. And then we also get everything that's required, the retention of sodium, the production of aquaporins, etc. And we're going to increase the blood pressure, blood volume, blood pressure. And if we do that, we'll increase EDV and release ANP, and life will be perfectly normal. Okay, so that's a big overview. And the next thing that we're going to do then is we're ultimately going to discover everything we need to know about pH in our next episode.